Okay, so it's my pleasure to present my recent work in entanglement entropy and phase space density, lowest Landau levels, and half BPS states today. And this work is based on the paper Shumidas, Sean Hampton, and I wrote a post to arXiv very recently. To begin with, I want to maybe give some a review of the well-known entanglement entropy. Entanglement entropy is a measure of the degree of quantum entanglement between two subsystems. And in the simplest case, we consider these two subsystems form is a partition of the complete quantum system. And then we have some, we have a group of operators that measure and give informations of this subsystem A, which we are interested. And then we can define the reduced density matrix of this subregion A by the reduced density matrix is provided by the eigenvalues of these operators OA. And then we can define, measure the quantum entanglement between this subregion A we are interested and its complement by von Neumann entropy defined in the last equation. And if this quantum system has a gravitational due, then we can evaluate the entanglement entropy by its the geometries in the gravitational due. For example, we have the very famous Ryu-Takayanagi formula that conjectures that the entanglement entropy of code of a subregion in the field theory can be evaluated by the area with the same boundary in a block with the same boundary as this entanglement as the subregion boundary divided by the 4G Newton. And we also have its extensions. And then, but we know that this Ryu-Takayanagi formula is, it gives a proposal of the entanglement entropy of a subregion in a field theory. So it's actually natural to ask what if this entanglement entropy, what if we have a subregion in the bulk and we want to measure the entanglement entropy, or in particular, what's the entanglement entropy of a codimension 1 spatial subregion in the bulk? This question is subtle actually, because in the gravitational due, the space-time is dynamical. So it's unclear how to partition this the space in the due. So to be concrete, we can consider a concrete model. Here we consider the half BPS sectors of n equal 4 super Yang-Mills theory on S3. And we know that this gauge theory is due to the LLM geometries. So before we consider the entanglement entropy problem, let me briefly review the ideas of this thing. And we know that the half BPS sector of n equal 4 super Yang-Mills theory on S3 has 6 adjoint scalar fields, phi 1 and 2, phi 6. And the half BPS operators take the form like the product of the trace of some complex matrix Z to some order JA. And here the complex matrix Z is an n times n complex matrix with its real part and imaginary part to be 2 of the 6 adjoint scalar fields, for example, phi 1 and phi 2, respectively. Then the correlators of shootable product of such operators and their adjoints can be calculated via quantum mechanical complex matrix model of this complex matrix Z. So we tentatively called it complex matrix model, and it's in Hamiltonian is shown in the last equation. Then for this gauge model, we can always choose a gauge. Hereby, we can decompose this complex matrix set into a unitary matrix U and an upper triangular matrix T. And the diagonal term of this upper triangular matrix T, we call it Z1 to Zn, and we call the off-diagonal term R. Then for we can rewrite this Hamiltonian into a Hamiltonian of particles moving in two-dimensional harmonic oscillator potential. And for these diagonal terms, we need to introduce a van der Waals determinant. So these n diagonal terms describes the n fermions. And for the off-diagonal terms, it's still symmetric, so it's used to describe the bosons. And the bosons are always in the ground state, so they do not contribute to the correlators of operators. So we only need to consider a fermion. Moreover, these fermions can be equivalently described by lowest Landau level states in terms of single-body lowest Landau level wave function, shown in the last equation. So now we have a duality shown here. We have a half BPS sector of n equal for super-Yang-mu theory, which is a gauge theory, and it has a gravitational theory due, which is LLM geometries, and the complex matrix model is like some subset of these half BPS sectors of sectors, and this complex matrix model is a quantum mechanical model. Then after fix the gauge, and second quantize it, we obtain the quantum field theory, which is the lowest Landau level. And now we can ask the question we asked before. What's entanglement entropy of a codimensional one spatial in this LLM geometry, and what does it mean in the half BPS sector? However, then we will face the same problem, same issue. That is how to partition the dynamical space. So again, it's unclear how to do that. So let's try another strategy. If we have an entanglement entropy in this, we have some entanglement entropy measured in this lowest Landau level. What does it mean in this complex matrix model? And then is there any physics quantities in half BPS sector and it's still that correspond to this entanglement measures in complex matrix model? So in this work, we focus on the first step from the entanglement entropy and this question exclamation mark, this part. And to study this thing, we need to introduce some very useful tools. The first one is the Wigner phase space density operator defined in the first equation. And in the classical limits, the expectation value of this Wigner operator is either 0 or 1, which is called Thomas-Fermi theory. And the integral of this phase space density operator, it's integral of the expectation value of this Wigner operator in the full phase space is the number of the particles. And then we can connect this Wigner operator with the correlation function and make the statement here. The correlation function is determined by the Fourier transform of the expectation value of the Wigner operator. Moreover, we can introduce something called the one-dimensional auxiliary system. So we know that the two-dimensional lowest Landau level field operator is shown in the first equation. Here, it is a sum of the anti-commuted annihilation operator times the single body lowest Landau level wave function, shown in the second equation. And here the late index L means represent the angular momentum, and 0 means it's in lowest Landau level. And in the right-hand side of this wave function, this L is, we use the convention to make it to be square root of 2 times the magnetic length. And we need to point out that it's not this psi, which is not this lowest Landau level field operator, but the sum of all lowest Landau levels and the remaining higher Landau levels that satisfy anti-commutation relations. So this psi and psi dagger does not satisfy the anti-commutation relations. And now we introduce the one-dimensional auxiliary system, this Z, to be the sum of the annihilation operator, which is in the two-dimensional lowest Landau level field operator, times some one-dimensional wave function. Here, the only requirement of this wave function is that this wave function zeta v need to form a complete orthonormal set in the real line. Then we can go back to the this two-dimensional lowest Landau level field operator and one-dimensional auxiliary system field operator are connected by some 1D, 2D kernel. We use curved K to call it. And below, we will choose this auxiliary system to be a one-dimensional harmonic oscillator, which means it's describing the fermionic theory in one-dimensional harmonic oscillator potential. This is a natural choice because considering that our goal is to solve some half BPS problem. So then go back to the Wigner operator, and before we said that the correlation function is determined by the Fourier transform of the expectation value of Wigner operator. Now benefited from the 1D, 2D kernel, we can slightly revise this statement. We can say the two-dimensional lowest Landau level correlation function is determined by the Fourier transform of the expectation value of one-dimensional Wigner operator via 2D, 1D kernel, which is shown in the right up corner. And then we can consider a finite disk with area NL square, which means they are first is occupied by the first, we have the first n lowest Landau level, and we consider this n to be large. And moreover, we consider a correlation function between 2 points that are far away from the edge. In this case, the Thomas-Fermi approximation is valid. So approximately the correlation function can be it's in the form of the last equation. And then we can use this correlation function to calculate the entanglement entropy. Klitsch and his collaborators have shown that the entanglement entropy can be expressed in a series of all cumulants. And cumulants is just the derivative of the grand canonical example. And furthermore, Calabrese and his collaborators have shown that in our case, all cumulants can be expressed by two-dimensional correlation function CA. Here, this CA is we restrict the point of correlation function into the subregion A. So in order to do this, we introduce indicator function 1, and this is a generalization of the Heaviside step function. So if the point is in A, which we are interested, then this indicator function will give 1. If it's not, then this indicator function will give 0. So that we will have a correlation function in subregion A called CA. And moreover, in large n limit, it's believed that among all the cumulants, the C2 dominates. and the higher cumulants only contribute the correction at the order 1. So that means approximately we can use the C2 cumulant as to calculate as the approximation of this entanglement entropy. So eventually we use the last equation to determine the entanglement entropy in our case. So after a huge amount of calculation, we find the right-hand side of the last equation will become an area integral like this. And the integrand is a series of Laplace operators, order of Laplace operators act on the indicator function. However, because the first term of this series is something like 1x in A times 1x not in A. So this thing will always vanish. That means we can always use Stokes' theorems to rewrite the integrand and make the integral into a line integral. And this series become the a series of different order of Laplace operator act on the boundary of the subregion A, which we call the partial A. Then for the local curvature of this partial A, if it's in the limit that the local curvature is much larger than its first derivative and much smaller than the inverse magnetic length, we can approximate the original curve of partial A by an arc with the radius inverse curvature. And then this Laplace operator just degenerate into just the second derivative of the radius. And then the right-hand side of this entanglement entropy can be exactly figured out. And the sum of all the series is convergent. And finally, we find the leading term of this entanglement entropy is equal to square root of pi divided by 6L times the length of the partial A, length of the boundary, which means is the perimeter of the subregion A we are interested. And this square root of pi over 6L is the non-trivial factor coming from the sum of all the terms of the series. So it's it tells us this is convergent. And however, if this condition is broken, then we need to consider all terms of the Laplace operator. And we see there are some terms like curvature multiply the first derivative of radius and curvature squared times the second derivative of angular variable. So that means for higher higher order of Laplace operator like Nabla's 4th, 6, and blah blah blah, then there's derivatives of curvature enters, and the sum of all these contributions due to the derivatives of curvatures will give a non-trivial order 1 correction. We call it corner contribution to entanglement entropy. To evaluate this thing, we considering the step function of corner with angle alpha. And we also introduce some exponential to minus epsilon r squared and make epsilon goes to 0 to avoid the divergence due to the infinite perimeter. And finally, we figure out the result in A alpha in the last equation. Here, the 1/12 factor comes from the coefficient of the C2 cumulant, which is pi squared over 3. And we compare our result with some earlier, more exact results done by condensed matter people in 2020. The red dots are their result, and the blue one is our result. And our result is like 2% to 3% deviation from theirs. We believe that's because we use only the first cumulant as an approximation of the entanglement entropy. So we have a 1/12 factor. But exact factor should not be 1/12. It should be there should be some correction coming from the higher cumulant. But the expression in the bracket, we believe that's exact. So at last, I want to we can think about how this entanglement entropy in lowest Landau level means in the complex matrix model. So first, we know that this lowest Landau level is second quantization of the it's after fixed gauge and second quantize the complex matrix model. So it's a field theory, but this complex matrix model is a quantum mechanical theory. So for quantum mechanics, the space is a point. So we cannot partition the space. However, we can partition the target space where the wave function can take value. So this is some target space entanglement. And moreover, in this specific case, we have already chosen a gauge, and from the previous the circle out part in red, we can rewrite it in the selected gauge. We will find that these operators of a suitable product of operators, they only depends on the diagonal terms of the upper triangular matrix, which means it only depends on the fermions. So the non-trivial partitions are partitions on the complex, or we can say two-dimensional target space of fermions. Then we can draw some conclusions due to our understanding of the target space entanglement. First is that in the target space, in this case, the Hilbert space should be a direct sum of n+1 sectors. We label each sector by capital N minus n, and which means their m fermions have their eigenvalues in subregion A, while the rest of them will stay in subregion A complement. And then operators restricted in A will also have n+1 sector. The representation matrix of this operator A will also have n+1 sectors, and the expectation value of these OAs should be a sum of the contribution of each sectors. Then from this OA, we can determine a reduced density matrix, and it's it's just like the entanglement entropy we reviewed at the very beginning of these slides. It's just provided by the eigenvalue of these operators. Then eventually we have the target space entanglement entropy defined to be the last equation. It need to be it should be a sum of the contribution from each sector, and each sector is each sector is it's a trace of each corresponding sectors of a reduced density matrix times the log of this sector of reduced density matrix. And we know because due to the second quantization relation between the lowest Landau level entanglement entropy and this target space entanglement in complex matrix model, this entanglement entropy we figure out should be equivalent to the result we figure out in lowest Landau level problem. So tentatively, this is what we have done now. We find that for lowest Landau level, we determine the entanglement entropy for arbitrary subregion, and we explain these quantities in the complex matrix model. And the next step is to consider what quantity it means in half BPS sector and its gravitational due. If fortunately it's still entanglement measured, then we will have a way to partition the LLM geometries, even though we have no idea, even though it's unclear how to do it visually. I mean, maybe we cannot see how we partition it, but this means we will have a way to partition it. So that's all. Thank you very much.